Thank you very much, Han. Thank you. I'm Alex Seifalian. I base in Division of Surgical Science, and currently my lab is on 9th floor of Royal Free Hospital. And we develop organ and we do some cancer research. So we set up a platform technology. Our platform technology based on developing material which on the nanotechnology base. This is nanoparticle and as well as synthetic material to make organs. We do work a lot on stem cell and bioreactor, which is like you make an organ and the noise. We put them together and to make organ. And we are a very multidisciplinary team. We're over 60 people up there. About 30 people research fellow and 30 academic, and we're making large number of organ, and some of this organ already gone to human as a compassionate case or we starting clinical trial. So nanoparticle, nanotechnology. If you see your hair, the diameter of your hair is about 300,000 nanometer. So that's the nano base on, So we working on in terms of 5-6 nanometer. So this is like a new technology being like in medical applications, say past 6-7 years, moving fast, And there's huge potential for nanotechnology. For example, here, we synthesize this nanoparticle. This is fluorescence nanoparticle. And if you inject this nanoparticle here in the chicken leg from M&S, and you could see it. This is just taken with mobile camera. So our first application here, to localize this cancer, to see if somebody have cancer or not, if somebody have lump in their breast, go to GP may send it to hospital. Usually they have to take a biopsy. And from sentinel node, then send it to histology, to pathology to see yes, cancer or not. To localize that biopsy to take is not very easy. They have to inject radioisotope to make radiation as well as blue dye to localize it. If we could inject that, we could inject it and it goes, we could see it by eyes, it's moving up, and it goes to local sentinel node, then we could take a biopsy. Or if we could even better, we attach a cancer antibody onto it, and it goes there, and if it's cancer, shine light, and if it's not cancer, disappear. So you don't even need to have a biopsy. And it doesn't even have to come to hospital. It could go even just GP and inject it, and that's it. They are different size, that means different penetration, different wavelength, and we work on this red one, this much penetrate much longer, and hence different color. And they are about 8 nanometer. So what we do, we get them, we coat them with our material we develop, and we attach an antibody. And this poor rat we induced cancer, colorectal cancer into it. We injected with antibody, it's all gone to cancer cell. If you see this, there's like seen in the conventional way, these flowers, when you put the nanoparticle in the water, it light up. So nanoparticle goes through. It's, so it's very small. When you inject into here, it goes up there. And this is a new technology, and I'm sure next 5 years will be one of the cancer diagnostic or treatment, which I'll come to it. So nanoparticle we synthesize up there. Is it here? We synthesize lots of different nanoparticles. Gold nanoparticle, silver, magnetic nanoparticle, and those nanoparticle, magnetic nanoparticle, again, it got huge potential. If you inject magnetic nanoparticle, if you manage to get it to cancer cell, put it in magnetic field, and then when you put the radio frequency on that field, magnetic particle is about 3 nanometers. So it seems to vibrate, and they get hot, and they kill the cancer cell about 50 degrees. We use silver nanoparticle as a bacterial resistance. So these days, if you go buy deodorant, even socks, It's got a little silver nanoparticle on it. It's anti-smell or anything. You know, more expensive as well. I don't know if it works or not. Nanodiamond. We use nanodiamond. We collaborate with Central Nanotechnology down the road, and for enhanced cell polar growth as well as is conductive. Well, one of the main applications we work carbon nanotube. Carbon nanotube now is everywhere. You know, carbon nanotube is like a carbon dust. You could see it. 50 times stronger than the steel, but it's as light as like a jacket. They use in aerospace a lot carbon nanotube or aeroplane wing made by carbon nanotube. Military you use a lot, and you could buy a bullet jacket suit carbon nanotube made, and it's bulletproof. But in medicine, and there are different kind of carbon nanotube. They're extremely small. I say 300,000 nanometer the hair, but carbon nanotube is about 3 nanometer. In carbon nanotube, if you shine this light to it, so if you inject the carbon nanotube in the cancer, you shine this light to it, in 40 seconds become 50 degrees, from 37 degrees become 50 degrees. And cancer cells die about 49 degrees. So again, we're working on that a lot. But our main expertise to make material, to make organ out of it. There are not many material you could put inside the body. You know, there's all this technology stuff. There's lots of material for other application to make case for mobile phone. But if you want to make something to put inside the body, there are not many around, you know, very few. And the one is around is not very good. So we synthesize material which can be inside the body. So we synthesize two kinds of material. One, it can be there forever, and one they biodegrade, that disappear gradually. The latter one, we tend to use it for pediatric, for children, but the first one for adult application. Material we synthesize, you know, like a chemistry, you know, you just making, you know. So initially, long time ago, we were studying a lot with Professor Parker's group, Natural Science Museum, and he used to give us this little butterfly's wing, and we grow cells on it. Initially, we want to see which pattern is good. We make that pattern, cell grows onto it, like making organ. Then, when we squash this butterfly wing, you know, there's nanoparticle in it. It could pass nanoparticle, this nanoparticle based on silicon, and we make those nanoparticles upstairs, we synthesize it, and then we mix it other one. At the same time, similar nanoparticle made by American Air Force to enhance the jacket when the people go to aerospace. So this, when you make a material, we call it nanocomposite, and so you mix them together and you can make anything out of it. Our nanoparticle we make is very hydrophobic. That means nothing can attach to it. If you make something like super hydrophobic and say coat your car, you never have to clean it, or window. So the glasses, if most of the glasses coated with super hydrophobic. In medicine, if you make super hydrophobic, nothing can attach to it. Then you can attach molecules to it, and you attach specific things to it, like the cells. The material we make is the strongest material in the market. So hence, you can make it really thin and it still be strong. So for like contact lens. And when you make a material, in surgery, you know, if you're going to implant in the body, you have to put in the animal model tested. We put it 3 years as a flat shield like this, done all the toxicity and an animal model, and say, yes, it's no toxicity, done, you know, no effect, no immunological effect, and we could make organ. So we started making organ, you know, making a lot of cell work. Here, one of our, Nicholas, one of our PhD students, he got now 3D printer. We used to make it manually. Now we could print organ. We could print ear, nose, whatever. You know, we could print. We got a printer here. You could see it, but we got a bigger and cell and organ printer upstairs. And when we make an organ, we want to make organ, we want cell grows into it. But usually, and we add salt or sugar, more or less, into the scaffold. This is our material. It's like a honey. We make the mold, we add those things, and then we put in the water, and salt and sugar comes out, and there are lots of little holes through it, and the cell could grow into it. This is talking about the butterfly. So for example, on our material, we got this pattern onto it. And this is on nano level pattern onto it. And this is scaffold, scaffold for making organ without pattern. And this with pattern, because cell grows much better on pattern. And this would collaborate with Glasgow, Professor Delpy. One of the things, you have to do some of the tests to see how it works. So we get our scaffold. This is our scaffold material. And we want to see cell grows into, tissue grows into. We got eggs. And we cut the eggs to push that through into the egg. And we got some stem cell from fat incorporated into it. And then put it in the eggs and in the incubator. And after a few weeks, you take it out and you can see blood vessel grows into it. And also we can attach peptides onto it so we could attract the stem cell. So one of the things we've done, and which currently we're going to start a clinical trial, we make artery for coronary artery and for the vascular. So this been developed in the lab and is taken to all the regulatory and currently fundable Wellcome Trust to do clinical trial for bypass graft in the heart and the vascular. So this is our graft. We manufacture it. We put in animal models, you see, and inside they become more endothelialized, and that's the cell type covered inside the blood vessel. And we're going to start clinical trial for the coronary artery in September. We're just setting up our manufacturing, and we've done few patients for the leg already. We're making heart valve. Heart valve go through the catheter rather than open the chest. So here it is like heart valve we make. This thing. So heart valve made from the scaffold, made from nitinol, is a shape memory. When you squash it down, you go back to original shape. We make the leaflet for it. And this is the leaflet made from our material. And this leaflet becomes endothelialized in the body. And that's the way it works. And that's our valve. We got a display over there. You could see it. And this is our animal study we're doing. And we do this animal study in Paris because it's much cheaper there to do. And so this actually, the valve inside there, you cannot see it because it's not opaque, and this is a valve in the pigs and functioning. So we have to run it for 9 months, and if this valve works very well, then we do clinical study onto it. So this valve gone through the catheter in the leg, push it up, and open it in the heart there. Here is the heart, and jump open. God. Can you push it manually? Thank you. And we make a stent. Our stent is, again, because same principle, it goes through the brain, when they get aneurysm, or we fill in the aneurysm. They went in the brain, become aneurysm. We fill it with certain material we develop based on nanotechnology. Next. Oh, sorry. And tear duct, I had a PhD student, surgeon, came from Zurich, and she said she wanted to do PhD with me, and that's great. She started, and she said she wanted to make tear duct, and I didn't know there was a problem with tear duct. Apparently, patients when they get cancer, they remove this part, and tear duct go away, and also trauma, people there. And if you tear duct missing, the tear just running on your face all the time, and not very nice. So she developed this tube here. Currently, if somebody tear duct missing, They use this tube called Jones tube, and it's about 4 centimeter and about 1.5 millimeter diameter. And they put it here. Imagine it break, it comes out, and it's not very nice. So she developed this from our material, this tube here, and it's black color because coated with silver nanoparticle for anti-infection, because exposed to the outside. And this is our first patient. This eyes, she put drain it into the nose, and that's it done. And that was done September 2010. And since then, she done 5 more patients, and all of them is patent. That means the hole is open and working. And this is the diameter. This here is the 800 micrometer. It's a big achievement. Something exposed to air in like a less than millimeter be functioning in this time. And one of the challenges we had, we were come from Karolinska Institute, which from in Iceland. They had a patient, and this patient had a cancer of throat. So his windpipe, cancer damage here, and that's the lung, and they want to trachea. And nobody, they took him to the United States, Harvard, Chicago, whatever. Nobody wanted to help him. So the surgeon came and said, could you make a trachea? And I had a PhD student, with my colleague, doing a PhD first year. And usually I just say yes without even thinking, yes, we can or not. And then I thought they're going to give us like years time to work. And they say she got, this patient got 1 week, otherwise going to die. And virtually they gave us 10 days to make a trachea. Because we had our platform technology, we had our material tested. So virtually I sent her back down to butcher to get some trachea to see what it looked like and, to make that, So we made the ring, similar ring shape, into ring, we make all this porous stuff. So we make inside it got ring, which is when it doesn't allow to collapse trachea. Between ring is porous, and here again we got someone to show over there, and she made that. And then we didn't have enough. They put a stem cell on the wall, and we didn't have enough time. Inside the trachea is a type of the cell called epidermal cell, and that's anti-infection and also mucus clearance and stuff. We didn't have time to get stem cell converted to epidermal cell. So what the surgeon did, he took some tissue from the nose, his epidermal cell, cut them small pieces and sutured inside it. And when they did implanted, and after 8 weeks, when put camera inside it to see this cell, and it was all epidermalized. It's a bit like a grass, a few things in a garden you do, and after a few weeks you come, it's all done. And this just showing that patient. So yes, we got our butterfly from the material we developed. We trying to develop organ which is unmet clinical need. Either is not there, or what is there is not good enough. And we are a big group, Hans, hopefully let us to come to his institute, all these people. And so we are a mixture of scientific and science, biology, chemist, engineer, physicist, and a clinician. And we got lots of group, a PhD, MSc. Currently we got lots of PhD students. And our funding comes from those, and one of those which have been very funding us, Role Free Charity, been very kindly. Thank you. Thank you.